Okay, welcome back. What I thought I would do now is tell you a little bit about the architecture for modern A to D converters with buses. And the buses that people typically use nowadays when communicating to peripherals, because they're so much slower than the processors, is a serial bus. And there are a couple of or three common serial buses in use today. Serial buses. Let's see, what do we got here? You can't see it. All right. How can I make this viewable? Oh, I know. How about, how do you do make zoom? White who? There you go. How's that? Let's see what we can find. Well, I know what to do. What I'll do here is I'll just tell you what's on there. This here is the serial portion. Down over here on the left is an 8-channel A to D converter. That says UART for Universal Asynchronous Receiver Transmitter. And these are timers. Over in here I've got a little area that says SPI. That's a serial a peripheral interface, SPI. And these pins are all pins that you might find around a microcontroller. In this case it's an Atmel 3U microcontroller. And it's got other stuff in it too, which we're going to ignore for now. So what we're talking about is a subsystem within the microcontroller that has to do with communication to the outside world using high-speed serial buses. Your UART, that's typically used for something like your RS-232 port, or what some people might call the COM port. A lot of people call it the COM port. The SPI, serial peripheral interface, that might be used for high-speed communication to chips. The chips typically have a clock they need, and they will give you what's called synchronous, because it's got a clock, serial communication, and that can be very high speed. The UART with its serial port interface can give you what's known as asynchronous. That means without a clock distributed serial communication. So a couple or three common serial communication interfaces that you have to care about when you're going to be a designer of computers. One, the UART, that's the serial port, your COM port, or your RS-232 interface, or your RS-422 interface, all through the UART. The other SPI, that's a serial peripheral interface, and that usually comprises a master and a slave. The slave will be your slave chip. The master will probably be something like your microcontroller. The I2C, or sometimes called I2C, that's an interface which gives you a couple or three, what they call two-wire serial interface, instead of SPI, which requires a clock that gives you a four-wire serial interface. This is a COM port. It's 9 pins, D connector. You'll find it on the back of a lot of PCs, especially desktops, but no longer on the back of laptops. There are variants. One of the variants is a 25-pin D-connect. This has been around since the 60s, maybe before. Typically what you find is there are a few different hardware control pins which may or may not be used depending upon your application. If you're hooking this to a modem, it's really good to know if the modem is got a carrier. So if you can hear the carrier, that's like the high-pitched whistling sound you might get from like a fax machine, you get DCD, the data carrier detect. You can have a receive and transmit data, RxTX, data terminal ready. That's a hardware line. Data set ready, ready to send and clear to send, and RI for ring indicate. Ring indicate will be flashing if somebody's ringing the phone. So you can tell the computer when the phone, when the phone's ringing. Hardware handshaking is in general done with these very low data rate lines that are asserted high or low. Typical values range from 0 to 10 volts, not just for the hardware handshaking, but also for the data. So when you want to convert from a microcontroller to something like 0 to 10 volts, you need a DC to DC converter. Typically these things are put into chips, mixed signal semiconductors. For example, Maxim sells a chip called the Maxim 233, and Max 233 contains a charge pump which will do DC to DC conversion for you so that you can go from 0 to 5 volts to 0 to 10 volts. A self-clocking code is a code that contains the clock. In an RS-232 transmission done in an asynchronous mode, you have what's known as a self-clocking code. Your self-clocking code gives you start bits and stop bits, and then data bits. This down here says B0, B1, B2, B3, B4, B5, B6, B7. These are your 8 data bits. I don't see a parity bit. I see one start bit. I see one stop bit. So that's 8 data bits, no parity, 1 stop bit. The symbol used to show the setup here is 8 none 1. 8 data bits, no parity, 1 stop bit. The stop bit and the start bit, they're called what are known as framing bits. And you always want a start bit and a stop bit so that you can essentially synchronize the data clock that's internal to the UART. The UART is going to have its own clock, and that clock has to be synchronized with the transmit clock and the receive clock for the peripheral. So for the peripheral, you're going to have another UART, and it's going to have its own internal clock. And those clocks need to be also synchronized, and they are also synchronized by the start and stop bits. You need the framing bits because you have to know what time interval to sample the square wave at in order to be able to figure out whether it's a 0 or a 1. If your framing bits are in error, then you'll be sampling at improper intervals. If you're sampling at improper intervals, like not in the middle of the timing interval, then you won't know whether you've sampled the correct bit, 0 or 1. And then you'll wish you had a parity bit, which determines whether you've got an error in the transmitted data word. Parity allows for the detection of a single bit error. And they're writing this as plus minus 12 volts, although I think nominal it's plus minus 10 volts. So when you transmit without a clock separate, you've got to have some way to encode the clock so the transmitter and the receiver can, well, synchronize. Now we compare against what I'll call the master-slave relationship of the serial peripheral interface. First of all, it's not 2 wires anymore. It's now 4 wires. That's a big deal. For short distances, it's not a big deal. But if you were driving cables around, it'd be a big deal. You know, go between buildings with 4 cables instead of 2, and it's a big. It doubles the cost of everything. But for very short range, you go at a very high speed. You can throw S clock. That's the serial clock out. MOSI means master out, serial in, and so here's the slave. I'm sorry, master out, slave in. So there's master out, slave in. Here's master in, slave out. There's master in, slave out. So they're paired. That's data. And then here's a a selector, a slave select, not slave select if you like. Not slave select might be more convenient because you don't need to keep the line energized until you want the slave, I suppose. There's a lot of this sort of not write enable versus write enable kind of things running around. Read not write, not slave select. Often wonder why it's always inverted like that. Here's a nice interface. We have something very similar to this in our microcontroller class. It's using the SPI interface. Not real standardized, but it's very common. You can buy chips like A to D converters or D to A converters with SPI interfaces. Yeah, it's a 4-wire bus. Very good for short distances. Supports a single master and a single slave. I'm sorry, single master, multiple slaves. So let's see. What do we use to choose which slave? It's this SS line. So now I can wire OR a whole bunch of clocks, inputs and outputs, and these slaves can go to a tri-state or high impedance state on these lines when they're not selected. When they become selected, you want to make sure only one is selected at a time. You don't want a bunch of people on the bus talking at once. That would be bad. And it's very clear that there's a single master, and it's the SPI master. That's going to be your microcontroller. So this is really good if you have a microcontroller communicating to a bunch of peripherals. Like here's this one. Probably has a register inside of it that holds the time and keeps it constant, so that when you update this once a second, it just talks for a brief amount of time with a new number, then goes and does other things. It's synchronous serial interface. It's a synchronous bus because it's got a clock. In fact, it's got clocks for both the directions, and you can communicate in both directions simultaneously. They call that full duplex. Can anyone here think of a half duplex bus? What would be a good example? Anything you may have seen that has half duplex? How about MIDI? Anybody ever hear of a MIDI synthesizer? MIDI synthesizers are keyboards. They have 5-pin interfaces. They call them circular DIN keyboards, and that's a simplex local area network connector. Each one has an input and each one has an output, and you daisy chain these things together. It's very good for consumer electronics. Very low data rate, 38 kilobits per second, but just fine for keyboard inputs and outputs. And normally the command is key on, key off, and a key number. Let's see now. 50 megahertz clocks are not uncommon. That's perfect for microcontrollers. 8-bit toaster controllers that run at a megahertz or 16 megahertz are common. And in its quiescent state, the tiny version of the Arduino runs at nanowatts. So it's, kind of neat to see something that is basically an invisible kind of processor, very small, runs forever on a small battery. Or if you want Ytricity. Ytricity, that's what powers the RFID tags, because they got a coil that resonates. And so if you're within range, you can get your little microcontroller to start to go. Ytricity stands for wireless electricity. Let's see now. Master out, slave in, master in, slave out, MOSI and MISO. MOSI and MISO. I love it. System clock, slave select. I guess you'd need one slave select for each slave. And then the question is, how many how many peripherals will you really have? Well, if you had 128 peripherals, maybe you could multiplex your slave selects. Maybe that's a way to go, right? You could use some kind of a mux or decoder, and then use a small number of bits to control a large number of right. If you, in other words, if you had a 3 to 8 decoder, then you could use one of 3 bits, and only one slave would be selected at a time. Right? So 3 to 8 decoders guarantee that only one slave will be selected at a time if you had 8. Of course, you could have a 4 to 16 decoder or a 5 to 32 decoder, whatever you like. That'll save you a bunch of bits, but then you need an extra chip, right? The decoder. Let's see now. I need a separate chip select or slave select for each slave. And internally, we're going to have to shift the bits out. Each time we shift out a bit, we'll have to cycle our shift clock so that the slave can get the clock and shift it into its shift register. And what do we got here? 3 separate slave selects with 3 separate slaves. And they're all sharing the same serial system clock, the same MOSI and MISO, and that's all clearly wired ORed. But the slave selects, you need 1 line for each slave. So master-slave relationship exists. What does that mean to me? It means the slave cannot take over the bus and work to communicate with another slave on its own. That's what that means. Let's see. Clocking modes. A 2-phase clock means you can output a bit on the rising clock and you can output a bit on the falling clock. When you have double data rate data, it does that too. So running on 2 phases means anytime there's a clock transition, you can get another bit on output, which essentially doubles your data rate. Let's see, what else we got here? Timing diagrams, how fun is that? Here's a 2-phase clock. I got a clock coming in here and another clock there. I don't think this timing diagram does much for me. I don't really want it. Trade-offs, okay. Good, point-to-point connections. I think it's high speed, broadly supported, no addressing in protocol, simple to implement, no acknowledgement. I don't know if I've gotten, because it's not communicating back to me, I could just deselect it and go to the next thing after I shifted in some data. So I don't really know what's going on at the other end. Right? No flow control. It doesn't tell me, oh, I'm overwhelmed. You know, if I'm sending data at a gigahertz, it had better take the data at a gigahertz, or else that data is just going to fall on the floor. Buckets of bits all over my clean living room floor. What good is that? So I got no acknowledgement, no error control, no flow control, no arbitration. Stuff had better just work. That's the bottom line. And I better use it within the guaranteed area of operation. That is, if it's only good for a gigahertz and I run it at 2 gigahertz and it stops working properly, I will never know except by seeing the, let's say, unintended consequence of my action. So what can I do? I can go to eBay and I can buy all this good stuff. Radios, sensors, LCDs, all this good stuff real cheap with SPI interfaces. Slap it onto my microcontroller and Bob's your uncle, as long as I use it right. All the SPU, all the MCUs, all the microcontrollers have the serial peripheral interface buses. Totally common. Then there's another bus. Maxim has it called a 2-wire protocol That's really good for things like temperature sensors. It's very inexpensive. You don't need more than 2 wires. That's cool. You don't have to worry so much about clocks coming out of things. You know, it's a kind of a nice idea. There's a spec for it. It used to be proprietary. It's not particularly high speed. And you can just wire or everything onto the bus. Can you see it? Maybe not so good. Anyway, what you do is you just wire everything onto the bus that you need. If you have to go further, this looks really blurry to me. Does it look blurry to you? You can take the I2C bus and you can repeat it or extend it, and you can add more peripherals. Let's see now. Put in temperature sensors, real-time clocks. What else can you put in? Serial double EEPROMs. That's a good one. So let's assume that you wanted the moral equivalent of a USB key on your bus so that you could store data, just like in a file system. You could throw your serial double EEPROM in there. It'll just blow it all in there so you can have a nice program stored for you in memory indefinitely, even after the power is off. So that's a nice one to have. You can buy all this good stuff. Let's see if I can get back out. I'll just tell you what some of this stuff says. I2C dip switches. So you can control the switches with the I2C bus. Speeds, not particularly fast. 3.4 megabits per second. Very inexpensive. It has 2 lines of clock and data. There is a bus arbitration scheme, a protocol. Let's see now. What else can I tell you about it? You get acknowledgments. That's a good time, right? Because now you have a proper way to determine whether data has been transferred. Slaves have to respond. Protocol. It has a bus protocol. Hurrah! So you tell the slave, you say, okay, wake up. It says, oh, I'm awake. You say, here's some data. It says, got your data. Good times. That's an acknowledgement. If it says, sorry, the data's bad, that's a negative acknowledgement. You can say, okay, here it is again. That's error correction. Automatic retransmission request protocol, ARQ. So with a proper protocol, you can envision the peripheral coming back and saying, please transmit it again. And that allows you a mechanism where you correct data. The rest is a bit of an electrical thing. Let's see, sampling on the rising edge. Patent silliness. Okay, ATmega, Atmel, ATM, Atmega, makes a bunch of processors, including the Arduinos. So Arduino processors are RISC processors, or 8-bit processors, and they're essentially all made by Atmel, a small microprocessor manufacturer. Let's see what else I can tell you about I2 buses. That's enough. Let's see a practical peripheral. You want to save? No. Yes. Oh. Too late. What's this look like? This is a 12-bit digital to analog converter with a double EEPROM memory. Okay. It uses the I2 interface. Oh look, it's the spinning beach ball of death. It's got a DAC. It's got a power on reset. It's got a 2-wire interface capable of doing high speed 3.4 megahertz mode, or 100 kilohertz mode, or 400 kilohertz mode. So you can get slow, medium, and fast. Different packaging. It's got this very small, look at this, it's a 12-bit, right? Check it out. 12-bit digital analog converter. Remember before we said, well, gee, our R2 network would need 12 bits for data, one for power, one for ground, minimum 14 pins, right? Minimum. And if you wanted a chip select, maybe more. And if you need 15 pins. So I'm thinking, wow, that's a lot of pins. Check out this package, 6 pins. And in fact, if you think about it, if you wanted to, you could have a 16-pin DAC, and it would still only need 6 pins. So there's this sort of interesting thing going on here. SDA, SCL, that's your clock. SDA, that's your data. So that's serial clock, serial data. Let's see now. VDD, that's your power. VSS, I guess that's your supply. V out, where's V out? Oh, here it is, V out. This is what it's outputting. A resistive string DAC. So this is probably an R2 network. Here's a DAC register, which is going to latch to the R2 network. He's got a charge pump in here, which allows him to take VDD and get your voltage range to change a little bit. Let's see, what else do we need here? Power on reset. Power on reset. Doesn't look like it's hooked to anything, but I'm sure it is. They just didn't show it. A0. He should tell me what A0 is for. This whole thing runs on 50 milliamps. I wanted to see what A0 was for. I was hoping for a description. Temperature characteristics. Let's see what else do we have. I'd like a principle of operation here. A0. Device address selection pin. So this is the moral equivalent of my chip select. This pin can be tied or can be actively driven by digital logic. The logic state of this pin determines what the A0 bit of the I2C address bit should be. Okay. I'm not clear on that. Analog output voltage, Vout, that's clear. Supply voltage. VDD is power supply for the pin. That's good. He says he wants to run the supply voltage from 2.7 to 5.5 volts. 5 volts is nominal. VSS is the ground. It's recommended that the VSS be tied to 0, so that's fine. So VDD is power. VDD is power. VSS is ground, and that's what it says here. That's good. Here's my output. That's fine. So now I've got A0, and it says I can tie it to VSS or VDD. So I guess if I tie it to VSS, what happens? Device address selection pin. This pin is used to select which... Oh, that's the address it's supposed to respond to off of the bus, I guess. Let's see, what else do we got here? Probably means you can have 2 of these wire-ORed together through the same I2 bus, and one would be wired to power and the other's wired to ground. After that, you'd have to start using some kind of logic to choose which one is going to respond, because they're each going to have a different address. Let's see, nonlinearity, differential nonlinearity, analog specs. What else do I need to know about this thing? The MPC 4725 is a single-channel buffered voltage output 12-bit DAC with non-volatile double EEPROM memory. The user can store configuration register bits, 2 bits, and DAC output input bits, 12 bits, in non-volatile double EEPROM, which means he has 14 bits of double EEPROM. When a device is first powered on, it loads the DAC code from the double EEPROM, outputs the analog output according to the program settings, and the user can reprogram the double EEPROM or DAC register anytime. Fair enough. Nice practical example of an I-squared output. Oh, here is his model for the network, the resistor network, and he's showing the load. Check it out. Each resistor is double the load of the next resistor. So it's not an R2 network. He says in power down mode he draws 60 nanoamps. That's an incredibly small amount of power. What else does he need to tell me? Input coding data. Device code 1100. It's apparently the address that he responds to, except for the A0 bit, which you can set to ground for 5 volts. So he's got a predefined address. In hex, I would call that I think that's a 12, right? Because that's 8 plus 4. If A is 10, B, that's a C. 10, 11, 12, yeah, that's a C. And so it's either C0 or C1 is the address hardwired into this chip. Then he needs 12 bits. Let's see now. Data bits 0 through 12. This goes into the DAC register, 0 through 11. And then PD, this is the power down select bits. It's quite a bit more complicated to use it in terms of software when you have a serial interface. Once it's been selected, it looks like you can stream data to the device. And after you're done with the device, it will using its double EEPROM, hold and register the data so that it remains constant on the output. Let's see, the charge pump initiates the double EEPROM writing sequence at the falling edge of the ACK pulse. Charge pump. The charge pump, I'm saying you need that for level conversion. What else do you need? Right, busy. Overview. 2-wire I2C serial interface, serial clock, generates start and stop conditions. I think the thing you do with a device like this is you go in and you wonder to yourself, what's it going to take for me to hook this up to my Arduino and make it work? And what you can find here is an Adafruit tutorial. And he gives you the full-blown software for hooking this to your little Arduino. He gives you a library, which is handy. Let's see if we can get it from our GitHub. Get it from Git. So this is the MPC 45. In a case like that, I would just download the zip files. It's always very convenient if you pick a chip where the software exists. right? Because why not? Open with 7-zip. So this is an Adafruit item. And I have C source code and examples for a sine wave and a triangle wave. Let's have a looky-loo. This should be opened with processing, or with the Arduino. For some reason, he can't seem to find the Arduino IDE. Did I not install it here? If not, then I'll have to open it with something else like Notepad. Open with... I'm a little surprised the... Let's see if Notepad can open this. Notepad not found. How does one use Notepad? Note... There it is. So if I rename this with a text, it still doesn't see it. Do you all know how to use Windows? How do you change this text so that it... How do you change this file so it ends with a .txt? I want to open this file. How do I open the file? I wanted to open with Notepad. Click on it. Cannot open file. Okay. Drag it to Note file. Oh, that's nice. Yeah. Well, the bottom line is you need like a something that knows how to read text. Is like WordPad on this system? WordPad. Okay. So what if I drag it to WordPad? There you go. So this is these are the values for a sine wave that have been hard-coded in. In Arduino parlance, you have to set up the baud rate for the serial port in order to be able to do things like print text. And that's what this does. It says serial begin 9600 baud, so when you run the program, you can actually get some feedback. And the first thing it does is it prints hello. He goes out with this thing called DAC begin. Now DAC came from this wire header and also from this Adafruit library. The Adafruit library apparently gives us a one-wire interface to this particular DAC, which we'd have to modify if we were going to change the DACs. So here's the address. For some reason I thought it was 1000, which is... That's not quite 6, is it? I thought that was C. 6 is going to be 110, right? So maybe you just got the first couple bits there. And then the least significant bit, that's the one you're going to assert. And he says here the address is changed depending upon what model you get. So the 4725A0 has 1 bit difference between its address and the 4725A2, apparently. So you have to assert which DAC you want on the bus. and that's DAC.begin giving you an address for the DAC. It's kind of interesting. I got a DAC set voltage that's going to output through the one-wire interface to the DAC. So you can sort of see why it's nice to have it handled for you. It's dealing with the I2 bus protocol for you at a low level. If later you want to change DACs because you've got a different address, it's easy. But if you're going to change DACs to something that uses a completely different protocol, then you've got a problem. Like an SPI protocol, this wouldn't work at all. Then he's giving you value lookups and outputting one word at a time. Looks like he's got different DAC lookup tables depending upon what the resolution of the DAC is. And I'm going to guess, yep, it's in a loop. So that's kind of cool. Here's a picture of the triangle wave that the DAC is outputting. And it's nice and smooth. I think you can probably zoom in on it. The little bumps that you get in here that are shadowed, that's anti-aliasing. So you can't trust this image as being accurate. It's been processed a little bit. I don't know what I just did by clicking on it. Visual Studio. What? A few minutes? I don't think so. That's silly. So when you're dealing with a bus, you've got to deal with some sort of a library or write your own software for doing bus communications. You can kind of see that when the software is already handled for you, it simplifies things greatly. I2C interfaces in the wire libraries are already present. So most microcontrollers already know how to talk to this bus. So you don't have to worry about it at the low level. The wiring of your little chip is usually straightforward. These are pull-up resistors for the bus. You'd probably only need one resistor per wire, and that's it. You wouldn't need one for every peripheral. The bypass capacitors are probably good to try and damp out some of the noise that might be on the power supply. Let's see what else you might need. Oh, here's somebody who threw in an amplifier. I guess that's good because your output, if you're going to hook it to something, should probably be relatively low impedance. So what that means is you could probably use this little comparator to drive a oh, that was fast, to drive a how you say, a speaker or headphones. And here you can see somebody has put in some relatively low-level software for driving the I2 interface, the I2C interface. That's one of the reasons why I selected it, is because I knew you'd be able to find some canned solution for a microcontroller. Picking a microcontroller peripheral out of the blue without thinking about software is a bad mistake. So when you're shopping for the right you know, A to D converter or D to A converter, it's really good to find out if others have done something before you and borrow the software. Because in general, you're going to have to change the software some, in order to make things work properly. Let's see, what do we got here? Current sense, voltage output. This looks like a motor controller. So we're using the DAC to control the speed of the motor. Let's see what else they got. Examples. Digital bipole control stepper. That's a current load. Oh, you can get development boards. That's another good thing to have. So if you got a development board, that kind of jump starts everything. And you can just wire that straight into your microcontroller and start to use it. And it even comes with software, so you can sort of mess about with it and make sure you understand its operation thoroughly before you get involved with a design. What else you got here? Blank pages. So I thought that was kind of neat. A reasonably good example. What else do we got in here? Okay, we don't have time for this, I don't think. We started at 11, right? 11, 12. We end at 1:30 here? Yeah, so we're practically done. You've seen the DAC now with an I2 interface. For the next thing that I was going to select is a kind of an overview of an A/D converter with an SPI interface. So you will have seen examples of chips that use both the I2C and the SPI. You can use either bus protocol with Arduinos. So whenever you get involved with microcontrollers, in general, it's really good to know if they've got support for any specific bus already. So we'll do a little bit of a review for the SPI microcontroller. What I did was I sent an email to the group, and I said, hey, why don't you guys look at this Google Sketch for doing 3D rendering of your printed circuit board designs? Because I did a Kickstarter project using a really cumbersome tool called Persistence of Vision. So when you look at my my project, my Arduino Shield, and you look at like the 3D rendering that I did, it looks really slick, but it came at a price. And the price is it takes several minutes for each frame. So it's one of those kind of old age batch jobs where you like start it today and come back tomorrow. And with Google Sketch, I expect the rendering is all done in real time. And you can explore the board by clicking on it and just dragging it around. But having said that, I never really tried Google Sketch. And I thought that it would be fun for you guys to try and do the setup on it. So let me see if I can find a nice picture. Yeah, that picture was rendered with Persistence of Vision, and what that means is the chrome in my little potentiometer is so shiny that you can see the reflection of the silk screen right on the potentiometer. How slick is that? But is that really important when it comes time to like figuring out if things are going to fit properly? No. And do I really need, it's one thing to do something like for Kickstarter and make it nice and spend the extra day, but it's another thing if you just want to get some kind of quick and dirty 3D rendering done. So I saw the alternatives available for 3D with Eagle, and I thought, wouldn't it be fun if we tried to do this with our boards? And so I sent out this little email, and what I'd like you to do is take a look at the email, the 3D Eagle stuff, and give it a try at home. You don't have to hand in anything, but I do want you to try it. And then what we're going to do when we come in next week is we're going to see if we can't do some rendering in 3D. Now, I'm not convinced that Google Sketch is going to be an easy setup for us. I understand there's going to be some learning involved, especially for me. And you might want to bring your laptops if you have them. Does everybody here have a laptop? Okay, we may like to try and have a little session, a hands-on session, and try and do some 3D rendering, because I think that would be fun. The Google Sketch thing, has anybody here ever tried Google Sketch before? It's a free program, I think, but only to a point. So they make it sort of non-free if you go beyond a certain number of components. Whereas POV is free no matter how many components you've got. And there's a very nice parts library. So if the part is present, well, in this particular case, that's an Alps potentiometer, and it was very specific, and we had to design the part for POV to get it to render this way, which is really a bummer. I mean, that's a lot of detail. With Google Sketch, maybe the libraries are a little bit better. Last thing you want to do is stop after you've done a nice printed circuit board design and then focus on doing something like designing the shape of your potentiometer to make it look like the one you want to buy. So that's kind of a bummer if you have to do that. And what I said in here is a 3D modeling program was used. What I didn't say was it was really hard, because nobody who buys something like this cares. They just want to see a pretty picture. So nobody has to know that this was tough, but it was. And I gotta say, it's none of that stuff is particularly easy. Oh, and by the way, I don't know if you noticed, my little Kickstarter thing, it's got up to like 5,300 bucks already, and we still have 23 days to go. So it's doing all right, you know, for a little geeky project. For whatever. I'd like it if you guys wanted to all like do Kickstarter projects. And I got a few people who are designing boards now. What do you think would be a nice board for us to design? Don't have to answer now, but think about it. I'll ask again next week. Some kind of a peripheral. This one does some basic stuff. What about if we used high resolution A to D converter and a high resolution D to A converter, like 16 bits, in and out? Wouldn't that be nice? Huh? I didn't think people would buy this. This is 10 bits in, and I'm using, the most rudimentary of output. People seem they're okay with it. But I have a feeling that if you had a high precision A to D converter and a high precision D to A converter on a shield, people would want it. We already know something about buses, SPI, I2C. We know Arduino buses support these things, and there are libraries for it. Very good to have software. So I'm thinking you could take a board and kick it up a notch. It doesn't have to be a board with $4 worth of parts. It could be a board with $12 worth of parts. And you don't have to charge like, $17 for a board. You could charge $24 or $30 for the board. Get a little profit margin in there. So when you start to think about these things, if you can actually charge more, like I got a new reward in here. I don't know if you noticed, but there's a $77 reward because of the bundle, which includes an R3 Arduino and two fully assembled shields to do stereo. Each shield is mono. It'd be nice to have a stereo shield. Gee, such an obvious thing. But it means redoing the whole board. So we can think in those terms. It's obvious to me there's no shortage of ideas, only a shortage of time. One of the students called me up from Brantford and said, I'm going to do a memory card and I want to do a Kickstarter project. Memory card for Arduino. Great idea. Once you start doing audio, you're limited in terms of the memory by how many seconds you can delay. If you only have 512 bytes of memory, your delays are trivial. But if you can go to, 512 bytes is nothing, right? That's what they have on the Arduino. If you can take a shield, plop it down, and put in 512 megabytes, hey, now you got something. And you can get a 512 megabyte chip for like nothing with with an SPI interface. So, hey, here's another Shield idea. So let's, there's no shortage of peripherals that you can add to a computer or things that you could do with it. Maybe somebody really wants memory. You can say, well, maybe I don't care about 16 bits worth of A to D converter and D to A converter, but everybody cares about memory. Adding memory to the Shield, to the Arduino with a little Shield, that just makes sense. Why not? So we could design memory boards. So we could have a whole line of products that come out. And I'll share with you some of the Eagle schematics that I used and Eagle printed circuit boards that I used for the audio shield that I've got here, so that you don't have to start from scratch. So that's all we have time for today. Thank you.